All right, so today we're actually going to solve the same shell balance that we've been solving for fluids in tube, but this time we're going to actually work with what's called BinghamPlastic. So BinghamPlastic is one of the non-Newtonian fluids.
Professor Martian?
Yes.
Could you upload the file?
I will. So, and I think there's one more. I uploaded all of the videos, correct? Yes. So and there is one more file that I owe you. Yes, I apologize. So I will upload both after this class. So BinghamPlastic essentially is a fluid that is in between fluid and a solid. It remains rigid until there is enough stress to move it. Okay. So there is a sort of a critical stress value, shear stress, up until which it doesn't move. So we had that joke before, if you did brush your teeth this morning, right? It takes a moment to squeeze, like it's not gonna, if you flip open your toothpaste and you flip it down, it's not gonna start flowing. You need to squeeze. Okay? So you can actually kind of keep adding pressure and squeeze more and more until you get that critical value for it to start flowing, despite of the gravity that would normally pull it outside. So cement is like that too until it settles. Toothpaste, drilling mud, ketchup, mayonnaise, and a lot of these fluids, they will have some that they're not always BinghamPlastic. Sometimes they're also shear thickening and shear thinning fluids, and we're going to go into those a little later. Kind of depends on the formulation and the modeling. So what happens with this and the way we model it, okay, we simply get our Newtonian fluid description and we shift it by this critical value tau 0. Okay? So if my tau yx, whatever shear stress is acting on the fluid, if it's larger in absolute value than this tau 0, then this is the relationship between my shear stress and velocity. If that shear stress is not high enough, technically I simply don't have a relationship because this fluid is not behaving as a fluid, it's behaving as a solid. So basically my fluid description stops. Okay? So we're gonna basically then, in that case, all I know is that derivative is simply 0. Okay? And that's it. So basically this tells me something about the velocity distribution, but that something is independent of the shear stress because shear stress is not high enough. And what this tells me is simply, okay, if fluid, this is inertia, if fluid was moving already in certain parts, it's going to continue moving, derivative is 0, at that same velocity without any kind of acceleration or anything. Okay? And if it wasn't moving, it's not going to start. That's essentially what this derivative is 0 means. It's like law of inertia, right? So I need 2 parameters, not just one. For Newtonian fluids, I need only one parameter to describe the fluid. That is that coefficient of proportionality, mu. I'm calling it now mu 0 just to differentiate it a little. So now I need both mu 0 and tau 0, otherwise my fluid is not fully. And again, it's important to understand that basically when my shear stress is not high enough, I have a solid and I cannot apply the same relationships that I can for fluids. So my description simply stops, and I have to be, math doesn't know it, right? I have to be the one to impose that. And mathematically, we'll still get some shear stress, and the relationship will actually, shear stress will look the same as in Newtonian fluid, like shear stress itself. It's just that in certain portions of the fluid where it's not high enough, it simply doesn't tell me anything about velocity distribution. Okay? I can't integrate it and get my velocity distribution. So that is the difference. Okay? And there's actually, let's see if this will, I don't know if the sound will, if the sound doesn't go, I'm going to play it next time. So there's this National Committee for Fluid Mechanics films. They're 1960s videos on fluid mechanics. So they're definitely dated. Okay? But they're excellent. Other than that, they're excellent. So let's look at the rheological behavior of fluids. And we're going to go to the, and when I say they're dated, let's see if the sound goes. Is the sound going through? Okay. It's not. All right. I'm going to do a quick switch. This is what I mean by dated. This is how professors looked like. All right. So I'm going to jump. So
we have marked a portion of a flow field outside the viscous bound.
So this is an entire video. I'm just going to show the one that it depends on, that is related to the Bingham Plastics, and I think I made note that it's. So let's just quickly see how is this going to affect our fluid profile. Okay, play.
In the steady laminar flow of incompressible Newtonian fluids through tubes, a single material constant, the coefficient of viscosity, governs the volume rate of flow and the velocity field. Here we get the familiar parabolic velocity profile. However, for more general fluids, the flow rate and the velocity field are governed by a viscosity function. For such a fluid, the velocity profile can be very different from parabolic. We have seen how nonlinearity affects shear stresses. It also has an unusual effect on the normal stresses. Here is some glycerin, and here is one of my wife's favorite recipes. Why does the cake batter climb the mixing shaft in contrast to the behavior of the Newtonian fluid? We can get a better idea of what happened there if we look at a simpler experimental configuration. This shaft is mounted to rotate inside the larger glass tube in a coaxial geometry. The shaft is a hollow tube with a hole through the wall. The force per unit area exerted by the fluid in the direction normal to this cylindrical surface will be indicated by the level of the fluid inside this manometer tube. The stress normal to the outer cylinder will be shown by the level of the fluid in this sidearm manometer tube attached over a hole in the outer cylinder. When the central shaft is rotated, a shear flow is established in the annulus. The polymer solution climbs up around the rotating center tube as the cake batter did. Because the fluid is so viscous, it took about an hour for the level of the fluid inside the tubes to indicate the steady-state stress difference. Note that the stress exerted by the fluid normal to the cylinder walls is greater on the inner cylinder than on the outer. This is in contrast to the behavior of a Newtonian fluid, where the centrifugal field alone governs the pressure distribution. Here is another apparatus where we can observe.
All right, so you can actually watch the movies are excellent. The only difference to 2018 is that your professor is actually the one that cooks and observes the batter in the kitchen. Anyway, all right, so basically the differences, so there are many differences in the fluids. There are two that are observed in this video. One is in that the velocity profile. So there was that velocity profile that was flat, and we're about to compute that. And the other one is that actually there is a difference in the stresses that are in an annulus. You have two different sides, and those stresses are not necessarily balanced, which causes this climbing of the fluid. So what actually happens is that, again, we have sort of crystal-like arrangements of some particles within the fluid. So these are typically fluids that have particulates inside. Right? So this structure, and it's not crystal, it's not fully solid, right? It's just that these particles arrange themselves inside the fluid. So it takes a moment to break that structure down and start flowing. Whereas in the regular fluid, if you remember that picture of viscosity, that Eyring's theory that we had when we were developing viscosity of a liquid, you have this constant rearrangements of molecules inside the fluid, so it's actually extremely easy to get it moving. And any force will get it moving down the road. So here there is this critical tau to break down the structure and actually start flowing the fluid. Okay? And that results, and we're going to basically compute this. So these are the difference between Newtonian and Bingham fluid. Our standard Newtonian fluid has a viscosity profile. I have a linear stress. If you remember, there was like dp dz times r over 2 was my stress, shear stress, tau rz, dp minus dp dz. So P0 minus PL divided by L. And here we're going to actually have a similar, this is just now half of the fluid instead of the entire thing. We're going to actually have a similar shear stress profile. We're going to get tau RZ that is pretty much the same as Newton. Okay, there's nothing different there. However, there is this critical distance at which my tau RZ is large enough in absolute value, and this is growing from 0 towards a value. So in this region where its absolute value is large enough, I'm going to have essentially a parabolic profile. However, in this region, there is no relationship between stress and velocity. And velocity is, all I know is that derivative of velocity is 0. So it basically stays the value that it is right here. Okay? And that's flat. And that causes this flat profile. All right? Ready to compute this? As long as I'm going to quickly switch. Okay. Getting there, I hope. Okay, so we are going to do BinghamPlastic. So Bingham, whoa, oh, back to that again. Sure. Back on timeline. We're back to this game of no device connected. Alright. I'm gonna stop recording for a second.